Welcome to this coding problem walkthrough. Today, we're tackling the popular LeetCode problem number 49, group anagrams. In this problem, we'll explore how to group strings that are anagrams of each other. By the end of this session, you'll have a clear understanding of the approaches and their complexities. Let's dive in. In this problem, we are tasked with grouping strings that are anagrams of each other. To clarify, two strings are considered anagrams if one string can be rearranged to form the other, meaning they must contain the exact same letters with the same frequency. For example, the words listen and silent are anagrams because they share the same letters in identical proportions. Our goal is to write a function that takes an array of strings and organizes these strings into groups such that each group contains only strings that are anagrams of one another. The result should be a list of lists, where each inner list represents a group of anagrams. It's important to note that the order of the groups and the order of strings within each group does not matter in the output. The input will be a single array of strings, and the output will be a list of lists as described. This forms the foundation of the problem we need to solve. To better understand the problem, let's look at the first example. Given the input array strs equals eat, t, tan, 8, nat, bat, the output is eat, t, 8, tan, nat, bat. Here's the reasoning: eat, t, and 8 are anagrams because they all contain the same letters, e, a, and t, with identical frequencies. Similarly, tan and nat are anagrams of each other, as they both consist of the letters t, a, and n. Finally, bat does not have any corresponding anagrams in the input, so it forms its own group. Remember, the order of the groups and the order of strings within each group is arbitrary, which means this output is valid even if the groups or strings are in a different order. Now let's consider a simpler case. If the input array is strs equals, which contains only one string, an empty string, the output is. Here, the empty string is considered an anagram of itself, since there are no characters to rearrange. This means the output contains a single group consisting of the empty string. Another straightforward example is when the input is strs equals a. In this case, since there's only one string and no other strings to compare it with, the output is a. This demonstrates that even single strings, whether empty or non-empty, are valid inputs and are grouped accordingly. Let's also discuss the constraints and additional considerations for this problem. The input array can have anywhere from 1 to 10,000 strings, and each string can have a length between 0 and 100. All strings will consist of lowercase English letters, and duplicate strings in the input should all be included in the same group. For example, if the input has multiple instances of the same string, such as ABC, all occurrences should appear together in a single group. Additionally, empty strings are valid inputs and can be grouped together. It's worth noting that the order of groups and the order of strings within each group does not matter, giving us flexibility in how we implement the solution. Finally, let's examine some edge cases that you might encounter. One edge case is when the input array contains only one string, such as strs equals ABC. In this situation, the output will simply be ABC. Another scenario is when all strings in the input are unique and do not form anagram groups. In this case, each string will form its own group. Conversely, if all strings are anagrams of each other, like in strs equals ABC, ca, cab, then the output will consist of a single group containing all the strings. You may also encounter inputs with multiple empty strings, like strs equals, comma comma, where all the empty strings are grouped together. Finally, for larger inputs with long strings, such as strs equals, *100, b*100, *100, the solution needs to handle these efficiently while ensuring that strings with the same character composition are grouped correctly. To begin with, let's explore the brute force approach for solving the problem of grouping anagrams. The intuition here is straightforward. To determine if two strings are anagrams, we can sort the characters of both strings and compare their sorted versions. If they match, the strings are anagrams. With this in mind, the steps for this approach involve iterating through each string in the input array, sorting its characters, and grouping strings that produce the same sorted result. While this approach is conceptually simple and easy to implement, it has notable inefficiencies. Sorting each string takes k*log, k, or k is the string length, and since we process n strings, the overall time complexity becomes n*k*log, k. Additionally, the space complexity is n*k, as we need to store the grouped strings. This makes the brute force approach less suitable for larger datasets, prompting us to explore more optimized solutions. Now, let's consider an optimized hashing approach, which significantly improves efficiency by eliminating the need for sorting. The key idea here is to group anagrams based on character frequency instead. Two strings are anagrams if they have identical frequency counts for each character. To implement this, we calculate the frequency count for each string, representing it as a tuple of size 26, corresponding to the lowercase alphabet. This tuple serves as the key in a hash map, allowing us to group strings with the same frequency together. The hash map's values then represent the grouped anagrams. This approach is notably faster, as calculating frequency counts for a string takes O(k), resulting in an overall time complexity of O(n*k). The space complexity remains O(n*k) for storing the hash map. Additionally, there's an alternative approach using prime multiplication hashing, where each character is assigned a unique prime number, and the product of primes is used as the hash key for grouping. While clever, this method can suffer from integer overflow with longer strings, making it less practical for real-world use. With these options in mind, the optimized hashing approach emerges as the most practical and efficient strategy. Sorting in the brute force approach, while simple, involves an O(k*log k) cost per string, which becomes computationally expensive for large datasets. On the other hand, hashing based on character frequency is linear, O(k), and leverages the efficiency of hash maps for grouping. While the prime multiplication hashing method is theoretically intriguing, its risk of integer overflow and higher implementation complexity make it less viable. The key insight here is that character frequency uniquely identifies anagrams, allowing us to bypass the sorting step entirely and achieve significant performance gains. This aha moment highlights the power of leveraging hash maps to associate frequency counts with their respective anagram groups. When considering trade-offs, the brute force approach is straightforward but inefficient, the optimized hashing method balances complexity and speed, and the prime multiplication approach, though unique, lacks practicality. In conclusion, the optimized hashing approach offers the best balance between efficiency and scalability for the problem of grouping anagrams. By using character frequency as the basis for grouping, we achieve linear time complexity for processing strings, making this approach well-suited for handling large input sizes. Its implementation avoids the computational overhead of sorting and the pitfalls of alternative methods like prime multiplication hashing. This strategy not only meets the demands of performance but also remains manageable in terms of implementation complexity, making it the ideal choice for solving this problem efficiently. The problem is to determine whether two strings are anagrams of each other. To clarify, an anagram is formed by rearranging the letters of one string to match another, using all the letters exactly once. A straightforward approach to solving this is by leveraging the idea that two strings are anagrams if their sorted versions are identical. To implement this, we start with input validation. If either string is null or empty, or if their lengths differ, we can immediately conclude they are not anagrams and return false. Next, we convert each string into a list of characters and sort them alphabetically. Sorting ensures that if the strings contain the exact same characters and the exact same frequencies, their sorted lists will match. Finally, we compare these sorted versions. If they are identical, the strings are anagrams, otherwise, they are not. After comparing the sorted strings, the result is returned as true if they are identical, or false if they are not. The pseudocode for this approach is simple. First, verify that the lengths of both strings are the same. If not, return false. Then, sort both strings and compare their sorted versions. If they match, return true, otherwise, return false. The key insight here is that sorting the strings is an effective way to validate anagrams, as the order of characters becomes irrelevant once they are sorted. This makes sorting a powerful tool for solving problems that require normalization of input, such as checking permutations. Sorting, however, is the most computationally expensive part of this method. The time complexity is dominated by the sorting step, which takes O(n log n), where n is the length of the strings. Although the final comparison is linear, O(n), its contribution is negligible compared to sorting. There are also several edge cases to consider. For example, the algorithm should account for case sensitivity. Strings like listen and silent are not anagrams unless the case is ignored. Additionally, the algorithm should handle non-alphabetic characters, such as numbers or symbols, and recognize that two empty strings are valid anagrams of each other. To optimize this approach, we can replace sorting with a hash map. By using a frequency count to track the occurrences of each character in both strings, we can compare the character frequencies directly. This reduces the time complexity to O(n), as we no longer need to sort the strings. The data structures used in these approaches are simple yet effective. In the brute force approach, a list is utilized for sorting characters, which ensures that the order of appearance is normalized. In the optimized approach, a hash map is introduced to store the frequency of each character. This is more efficient for large inputs, as it avoids the overhead of sorting. To visualize the brute force approach, consider the strings listen and silent. First, listen is sorted into the list E, I, L, N, S, T, and silent is sorted similarly into E, I, L, N, S, T. Since these sorted lists are identical, the algorithm returns true. Meanwhile, in the hash map approach, we count the frequency of each character in listen, for example, L appears once, I appears once, and so on. Next, we compute the frequency of each character in silent, which is also S1, I1, L1, E1, N1, T1. Comparing these two frequency maps shows that they are equal, confirming that the strings are anagrams. The hash map approach is not only faster due to its O(n) time complexity but also scales better for larger inputs. By leveraging hash maps, we avoid the computational cost of sorting while achieving the same result, making this optimized method a preferred solution for checking anagrams in most scenarios. This solution groups anagrams efficiently using Python's default dict. The group anagrams function takes a list of strings as input. First, we initialize a default dict to store lists of anagrams grouped by their sorted forms. The core of the logic is in sorting each word from the input list to generate a unique key for its anagram group. Any words that are anagrams will have the same sorted key, so we append them to the same list in the default dict. Finally, we return all the grouped anagrams as a list of lists using anagram_map.values. This approach is efficient, as the sorting operation for each word is relatively fast, and the overall time complexity is approximately O(n*k log k, where n is the number of words and k is the average length of each word. The use of a dictionary ensures constant time lookups and insertions, making the implementation both simple and performant. This Java implementation mirrors the logic of the Python solution for grouping anagrams. It uses a hash map to group words by their sorted character representation. Key differences include explicit type declarations, the use of Java's char, and arrays.sort for sorting, and the map.putIfAbsent method to simplify adding new keys. The final result is returned as a list of lists using new ArrayList, map.values. We begin the solution by initializing a data structure called anagram_map, which is a default dict of lists. This will help us group words that are anagrams of each other. Starting with the first word in the input, eat, we sort its characters alphabetically, which gives us the key AET. We use this key to group all anagrams together, so we add eat to anagram_map under the key AET. Now, anagram_map contains one group, AET, eat. Next, we process the word t. Sorting its characters also results in the key AET. Since this key already exists in anagram_map, we simply add t to the existing group, making the map AET, eat, t. Continuing to the next word, tan, we sort its characters to get the key ant. This key does not yet exist in anagram_map, so we create a new group and add tan to it. The map now becomes AET, eat, t, ant, tan. Then, we process the word 8. Sorting it gives us the key AET, which already exists in the map. So, we add 8 to the existing group, resulting in AET, eat, t, 8, ant, tan. For the word nat, sorting it again gives us the key ant, which matches an existing group. We add nat to this group, updating the map to AET, eat, t, 8, ant, tan, nat. Finally, we process the word bat. Sorting it gives the key ABT, which is new. We create a new group for bat, and the final state of anagram_map becomes AET, eat, t, 8, ant, tan, nat, ABT, bat. Once all the words are processed, we move on to the final step, which converts the values of anagram_map into a list of lists. This gives us the result, eat, t, 8, tan, nat, bat, where each sublist represents a group of anagrams. Now, let's consider another example where the input is ABC, ca, cab, xyz, zyx, def. First, we initialize anagram_map as an empty default dict of lists. For the word ABC, sorting its characters gives the key ABC. We add ABC to the map under this key, resulting in ABC, ABC. Next, we take the word ca. Sorting it also gives ABC, so we add ca to the existing group, updating the map to ABC, ABC, ca. For the word cab, sorting its characters once again yields the key ABC. This matches an existing group, so we add cab to it. The map now becomes ABC, ABC, ca, cab. Next, we process the word XYZ. Sorting it gives the key XYZ, which is new. We create a new group and add XYZ to it, updating anagram_map to ABC, ABC, ca, cab, XYZ, XYZ. Then comes ZYX, which, when sorted, also produces the key XYZ. We add ZYX to the existing group, resulting in ABC, ABC, ca, cab, XYZ, XYZ, ZYX. Finally, for the word def, sorting gives the key def. We create a new group for it, and the final map becomes ABC, ABC, ca, cab, XYZ, XYZ, ZYX, def, def. To get the final result, we convert the values of anagram_map into a list of lists, resulting in ABC, ca, cab, XYZ, ZYX, def. Now, for our last example, the input is a. We initialize anagram_map as an empty default dict of lists. For the word a, sorting its characters gives the key a. We add it to the map under this key, resulting in a. Finally, we convert the values of anagram_map into a list of lists, which gives us a. This demonstrates how the solution works even for edge cases with single character words or minimal input. To analyze the time complexity of the solution, let's break it down into its key operations. First, we need to iterate through all the words in the input list strs. If there are n words, this contributes an O(n) factor. Next, for each word, we sort its characters using the sorted function. Sorting a word of length k takes k log k time. Since we perform this operation on all n words, the total cost of sorting is k log k. Finally, when we insert a sorted version of each word as a key into the dictionary and append the original word to the corresponding list, the average case time for these dictionary operations is 1 per insertion, which adds up to n overall. Combining these steps, the total time complexity of the solution is dominated by the sorting step, resulting in k log k. Now let's look at the space complexity of the solution. The main contributor is the hash map or dictionary, where each key is a sorted string of length k, and the values are lists of original words. In the worst case, where all words are unique anagrams, the dictionary could store up to n entries. The space required for the keys is k, and the space for the values, which include the original words, is also k. Additionally, the sorted function creates a temporary list of length k for each word during sorting. However, this space is not cumulative and gets reused, contributing only k at any moment. Finally, the input list SCRS and the output list of grouped anagrams each require k space. Combining these, the total space complexity of the solution is k. When comparing the optimized solution to a brute force approach, we can see a significant difference in efficiency. A naive method would involve comparing each word with every other word to check if they are anagrams, either by sorting or using character counts. Sorting-based comparisons would take n squared k log k time, while character count-based comparisons would require n squared k. Both are far less efficient than the optimized solution. The optimized approach avoids pairwise comparisons altogether by sorting each word to create unique keys in the dictionary, reducing the complexity to n k log k. Grouping anagrams is made efficient through the use of constant time average case dictionary operations. Whether in the best case, where all words form a single group, or the worst case, where every word is a unique anagram, the time complexity remains consistent at n k log k, and the space complexity remains n k. The mathematical justification for the big O complexity ties together the key operations. Sorting each word takes O, k asterisk log, k, iterating over all n words contributes O, n, and dictionary operations require O, 1, on average per word, resulting in a total of O, n, for insertion and retrieval. When combining these, the dominant term is the sorting of all the words, which gives us the overall time complexity of O, n asterisk k asterisk log, k. This dominance is why sorting drives the computational cost, and other operations remain secondary in their impact. When solving the group anagrams problem, there are several common mistakes to watch out for. First, neglecting edge cases can lead to incorrect results. For instance, scenarios like an array containing empty strings, single character strings, or strings of varying lengths must be handled properly. An example input such as a yub should still produce the correct grouping. Another common pitfall involves ignoring case sensitivity, which can cause mismatches. Standardizing all strings to either lowercase or uppercase ensures consistent comparisons. Efficiency is another area where mistakes occur. Naive implementations that repeatedly sort strings can result in excessive runtime complexity, especially for large inputs. Using a hash map-based approach can significantly reduce redundant operations. Additionally, be cautious when working with hash maps. Mutable keys like lists are invalid and can raise runtime errors. Finally, while optimizing for runtime, don't overlook space complexity. For example, creating multiple copies of sorted strings can unnecessarily inflate memory usage, leading to suboptimal solutions. Now, let's consider some key insights for interviews. A major part of solving this problem is recognizing patterns. Sorting strings or counting character frequencies with hash maps are common strategies that help simplify the problem and reduce complexity. Interviewers might assess your ability to pivot from a brute force approach to an optimized solution. Scalability is another important topic. You should be prepared to explain how your solution handles increasing input sizes and why you made certain design choices. For instance, opting for hash maps over sorting or discussing ways to minimize space usage. Additionally, interviewers may introduce variations of the problem, such as asking you to find the longest anagram group or process anagrams from a stream of strings. These tweaks test your adaptability and problem-solving skills. Finally, it's helpful to explore related problems, such as valid anagram or find all anagrams in a string, as they often share similar concepts and can provide valuable preparation. Let's examine some alternative approaches for tackling this problem. A popular optimized method is using a hash map where the key is a frequency count of characters, represented as a tuple of size 26 for lowercase English letters. This avoids the overhead of sorting strings repeatedly and improves performance. However, the trade-off is a slight increase in space usage to store these frequency counts. Another approach involves character count encoding, where character frequencies are converted into a unique string or tuple representation, such as A2B1C0, Z0. This also eliminates the need for sorting but may require extra pre-processing to address edge cases, like handling Unicode characters. Lastly, the sorting-based approach is a simpler method where each string is sorted, and the sorted version is used as the key in a hash map. While this method is straightforward to implement, it has higher runtime complexity, particularly for large inputs, due to the repeated sorting operations. Each approach has its trade-offs, so it's important to choose the one that best fits the problem constraints and requirements. Great job! To wrap up, we covered the group anagrams problem and explored an optimal solution using hash maps. Remember, this approach balances time and space efficiency while leveraging key concepts like sorting and frequency counts. Thanks for watching. Be sure to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!